So in our last video, we went over the 1D CNN architecture model for our Bird Song Classifier with the machine learning project I've been working on. And as a recap, our best performing model from 1D CNN was using MFCC plus RMS plus spectral centroid plus the continents embedding, where the output shape of the embeddings are 2. And with that, our training accuracy was 97% and validation accuracy was 91%, which was much better than any other model we've run in the past, such as feed-forward neural network, where our highest validation accuracy was only 75%, and certainly much better than any other traditional algorithm we've run, such as logistic regressions, multi-vector machine, and the tree-based models. So here's the learning curve and the confusion matrix, which I went over in our last video. And for hyperparameter tuning, I am going to use Hyperopt. So here is the Hyperopt documentation. Essentially, the first thing is to define the objective function, and then we define the search space, and then the Hyperopt will try to minimize the objective over the search space. And for our purpose, our objective function would probably be the loss function in our model, and then the search space will be the hyperparameters, and the Hyperopt will try to minimize the loss while searching over the hyperparameters. And I also looked at this Towards Data Science article, which they went over how to use a Hyperopt for hyperparameter tuning for their LSTM model. So first, they define the space, which is the hyperparameters they want to tune, and they defined the objective function. So in their case, it's an LSTM model. In our case, it will be a 1D CNN model. And at the end of the day, they got the lowest validation loss from the training, and their objective function would be to minimize this validation loss. So I already ran a model on our 1D CNN, and I will show you right now. All right. So I ran everything in Google Colab. I just downloaded it and put it into Visual Studio Code. So here is the same model that we've been using for the 1D CNN models we've ran. And all I did is I imported the Hyperopt library, and then I imported a bunch of things from the Hyperopt library. And the first thing is we load the features and labels, and then we shuffle the data, and then we create the sample weights. And now we're ready to create the model for the hypertuning. So I'm going to skip over these. These are the same stuff we've done before. And we create the audio features for training and validation. So the first thing we want to do is to define the search space. As we can see here, there's a bunch of hyperparameters that I want to tune. For example, learning rate, number of layers, the filter size, kernel size, strides, etc. And some of them I am going to have Hyperopt draw from a uniform distribution within a certain range. Some of them I am having Hyperpod choose from a set of choices. And here's where I define the objective function. So the first half of the object function should be very, very similar to what we've done in the past. So essentially, we create the audio features, and then we create the location features, which is the continents embeddings with the output dimension of 2. And then we concatenate the audio features and the continents features so that our output shape is our input shape is going to be the number of samples, and 251, which is the number of frames, since we have 8-second samples. And then the features will be the audio features plus the continents. So our audio features is 22 because we have 20 MFCC plus 1 RMS plus 1 spectral centroid, and then plus 2 for the continents. So our shape would be number of samples, 251, 24. Okay, and then here is where I am, passing in the parameters, and the parameters are the hyperparameters that I want to hypertune. And so in our objective function, I pass in the params, which will be the space. And I can get the different hyperparameters by indexing into the params dictionary. So for example, we can get the params learning rate, the params layers, the dropout, the dense. Dense is the number of nodes in the last fully connected layer, and then the batch size. And I actually realized that this should be a layer since I created the variable, might as well use it. But it's the same thing since I'm just previously I was just using the params layers. So here what I'm doing is saying, okay, so say for example, we have 2 layers, and this for loop is going to loop through the 2 layers starting from 1. So I'm going to loop through 1 and 2, right? So in our first layer, I'm going to dynamically get the filter kernel, stride, and pool. So it will be filter _1, kernel _1, etc. And I'm going to pass it into our conv1d layer, where I am going to use, again, indexing the param dictionary by passing in the filters _1 key. So here I am going to say, okay, Hyperopt is going to choose from the params filter _1, which is here. It's going to choose from any of these 3 choices. And then similarly for the kernel size strides, and I am going to also change the name of the conv layer dynamically. And again, we have the ReLU activation, and the regularization strength again is also indexed from the params dictionary. And then after that, we have the max pooling layer. Similarly, we get the pooling size and then the dropout layer. So after the model loop through 2 or 3 number of layers, depending on which one Hyperopt chose, based on the hyperparameter space that I defined up here, is going to create a fully connected layer, and by getting the number of nodes from the dense, which is this hyperparameter in the space, it's going to choose from any of these 3 choices. And then we will have the final dropout layer, and then we'll have the final classification layer. And I'm going to build a model, compile the model, where I'm passing in the learning rate, which is another hyperparameter. And then I'm going to fit the model. To fit the model, I first define a callback, and then I passing the features and the labels and the sample weights, and also batch size is also a hyperparameter that I'm tuning as well. And then after the model has been fit, I am going to get the best epoch, the best accuracy, and our objective function is to minimize the validation loss. So I'm getting the lowest validation loss from the entire epoch, and I'm going to return the lowest validation loss and the params for this lowest validation loss. And now that we have defined the search space and the objective function, we're going to call the trials, and then this is where we use Hyperopt to bypassing in the objective function, the parameters, and the algorithm is going to be TPE, and the number of maximum evaluation is going to be 50. So it's essentially it's going to create 50 models and using different hyperparameters, and then trials. So this is going to search in the hyperparameter search space to find the best hyperparameter that minimizes the validation loss. And this actually took around 4 hours to run. And at the end, our best loss was 0.21. And we can get the best parameters that's associated with the best loss by using a list comprehension here and calling the params, indexing to the params, and here is our best params. And we can see for our best params, we have 2 layers. And for the first layer, we have 256 nodes, and the second layer, we have 32 nodes. Since we only have 2 layers, these filter 3, kernel 3, all these are not actually being used since we only have 2 layers. Okay, and then I'm just going to get the best params by indexing into the best params dictionary. And I will pass in all the params into our function, into our build model function to actually train the model using the best params. So this is the same model that we've been using in the past. The only difference is I passing all of the hyperparameters as we have found from Hyperopt. And then we fed the model. And here is where we trained the model. And we can actually take a look at architecture real quick. So everything, from up until the input is the same as what we've seen in the past. We have the audio features, we have the continent features, and then we concatenate them to create number of samples, 251, which is the number of frames, and then 24, which is the number of features. And then we pass it to the conv1D layer, which has 256. The filter size is 256. And then we pass it through the max pooling layer, then the dropout layer, and then another conv1D max pooling and dropout layer, and then the fully connected layer at the end, and then the final dropout layer, and then the classification layer. So from this, we can see our actually training accuracy was 94%, and our validation accuracy was 89%. And here's the classification report and the confusion matrix. This actually is performed worse than our best performing model. Remember, our best performing model was 91% validation accuracy. So obviously, this is not an exhaustive search. So it's only searching based on the, I'm just going to scroll up real quick. It is only searching based on the hyperparameter space that I have already predefined. And it's only searching up to 50 times. So, if we had defined the hyperparameter space to be larger and the number of evaluations to be larger, potentially the model could have found a better hyperparameter. But this is just for experimentation. I just wanted to try this out. So, it's okay, even though at the end of the day, our validation accuracy was actually not as good as our initial try. That is all right. And yeah, so that's it for this video of hyperparameter tuning on the 1D CNN model using Hyperopt. I hope you will tune in to future videos as well. Thank you.